Hi, this is Davidson Potts, and this is lab 2 projectile motion. So, the introduction, the purpose of the lab. The purpose of this experiment is to observe the motion of an object that is thrown and moves like a projectile in 2 dimensions. Then to compare the observations using 2 different interfaces, Tracker and WebPython. And WebPython, we get 2 different computational models of with and without drag. So, an introduction to fundamental physics principles. So, projectile motion is the object follows a parabolic trajectory under the influence of gravity. In this case, the mass is a crumpled paper ball. Newton's second law is the motion is governed by forces, primarily gravity and air resistance. Um, the resisted force opposes motion and is proportional to the square of the velocity and terminal velocity. If air resistance is significant, velocity approaches low, where forces are balanced. And you can see that it's pictured down here. And this is how you calculate drag. So we're going to use 2 models, Tracker and WebPython. WebPython is where we put the code in place, and it'll generate models and graphs. Tracker generates graphs based on data collection with calibration, coordinate system, massive system, center of mass, all that sort. The video of a frame-by-frame analysis. So a brief preview of what the outcome of the experiment is. The methods with drag and gravitational force will be more accurate. So better captures what the motion with net forces acting on the object. With only gravity, the object will move in perfect parabolic motion, but this is not the case, and the drag force and terminal velocity need to be accounted for. In the computational model with drag, a more realistic trajectory is shown where the ball decelerates more rapidly due to drag, leading a shorter horizontal distance. So here are the experimental conditions. The system is crumpled a piece of paper. Surroundings, you have earth, gravity acting on the object, air resistance, and floor is the reference. And we assume that there's turbulent airflow and neglect effects from variations in air density. So we set up the coordinate system as the floor. Source of air that we'll talk about later is parallax, how it's not perfectly parallel to the ground. And that's the starting point, 0.625 meters. And then we analyzed the video that we recorded step by step. So these are the outcomes, the graphs you'll see here. This demonstrates net forces acting on the object. You can see it's not perfectly horizontal, constant over time, the negative slope because it's in the negative x direction. This projects the motion correctly in both directions on the graphs, and the motion is not perfectly constant in the x direction, as I just mentioned. Here are the initial conditions, key takeaways. They're basically almost the same in the sense, but B is a constant and is collected by trial and error of trying to match the horizontal x direction distance. So here's the while loop we used. There's also initial conditions and the graphical code that is not important to include or note. This is the while loop that iterates over 0.041 seconds. So there's a lot of iterations between 0.8333 seconds. That's between the tracker data. So this calculates the motion over time and the position. And drag can be updated to the velocity update formula and also fnet by just adding it simply. And it's also calculated in the equation here using the equation that we talked about earlier. So you can see that the horizontal distance is much longer in the only gravity model, and in the drag and gravity model, it's much shorter. Ignore the error that the iterations went over. They went over the ground. Excuse me. And so if I didn't shorten out the iterations in the time. Here's the model. Another error is that the tracker model with the parallax could not source that the height was 0.625. So that's the starting height for the computational models, which I could have put as 1.6 or so what this was, and seen the same motion of blue and red. They follow the same path, but they just have a different height and starting point. So that's the only error there, but you can see that much longer. This is much more accurate. So possible source of error, as mentioned before, tracker is not completely accurate, as new change in position with every iteration or frame when deciding this frame's parallax error. Here's not perfectly perpendicular to the motion plane. I was not able to plot the correct initial height numerically as seen in graph 4. And if the paper ball spin, this could have been an error, but it could have changed the trajectory. Drag coefficient is constant in this case, but may change with speed or air conditions. So what does this mean? Since our experiment likely does not allow enough time or distance for terminal velocity to be reached, a more suitable experiment would be involving dropping an object from much higher air resistance, like a coffee filter or a parachute, from a much greater height. So this will allow the object to reach an actual terminal velocity that can be calculated as air resistance builds up and counteracts gravity over a long duration of time. The paper doll did experience terminal velocity, but it's much harder to account for in this case. So what if the object were thrown straight up? If the object were initially thrown straight up with the same initial speed as the original experiment, the total time for it to return to the ground would be longer than the original experiment. This is due to the fact that the object must first accelerate to zero velocity at its peak of the motion before accelerating back down. And you can use these equations to calculate it in that instance. That's all.